All right, let's dive straight into this explainer. Today, we're basically booting up a mental diagnostic HUD to make the invisible forces of the physical world totally visible. Have you ever looked at a chaotic car crash, or even just a weirdly shaped object spinning through the air and wondered how physicists make any sense of it? Well, we are going to build a mental framework that acts like a literal superpower, letting you cut through all that noise to predict exactly how complex things are going to move.
Think about the difference between a simple, particle-like motion and a totally chaotic system. If you toss a regular ball into the air, it follows this beautiful, perfectly predictable parabolic curve, right? Super simple. But imagine throwing a baseball bat. It flips wildly, end over end, and every single part of that bat is taking a different, complicated path. It seems practically impossible to track, but here is the ultimate physical cheat code for understanding complex motion. If you map it out, there is one specific point on that spinning bat that follows the exact same smooth parabola as a simple tossed ball.
So here is our diagnostic boot-up sequence for the day. 1. Finding the center of mass. 2. Momentum and Newton's law. 3. The physics of collisions. 4. Conservation of linear momentum. 5. Analyzing types of collisions. And finally, 6. Rocket science and varying mass.
Section 1. Finding the center of mass. Let's start by unlocking our first diagnostic tool.
Imagine for a second that you could mathematically crush a massive, bulky object down into a single, infinitely dense point. That is essentially your center of mass, or COM. It's defined as the unique point in a system that moves as though all the system's mass were concentrated right there and all external forces were acting directly on it. So the really crucial takeaway is that no matter how wildly an object is spinning around, just like that baseball bat, this single holographic dot tracks perfectly through space, exactly like a simple particle. This quote really hits the nail on the head regarding the power of this concept. The center of mass of the bat moves as if the bat were a single particle of mass, m, with net force acting on it. Once you find that center of mass, you can predict the entire system's overall trajectory. You don't even have to worry about the thousands of chaotic rotations happening around it. You just apply the rules of physics to that one glowing dot. Section 2. Momentum and Newton's law. Now that we've got our target locked, let's look at the forces actually driving it.
To really understand movement, we absolutely have to talk about linear momentum, which physicists represent with the letter P. It's beautifully simple, just an object's mass multiplied by its velocity. In our mental HUD, you can visualize this as a glowing neon vector, an arrow, pointing exactly where the object is traveling and carrying the weight of the object's mass along with it. A heavy object moving super fast, that's got a massive, long neon arrow. A light, slow object, just a tiny one.
And this brings us to a massive upgrade for our classical physics toolkit. This is Newton's second law applied to a whole system. F net equals m times a com, meaning the net external force on a system equals its total mass times the acceleration of its center of mass. This is the math that links external pushes and pulls directly to the changes in our neon momentum vectors.
Now we need some ground rules to build our system boundaries. For these diagnostics to work, the system has to be closed, so no mass coming in or out. But here is the kicker. Only net external forces can accelerate the center of mass. Internal forces do absolutely nothing to it. Think about a firework exploding midair. The forces violently blowing it apart are purely internal to the firework system. So, incredibly, the center of mass of all those scattered, burning fragments continues on the exact same parabolic path as if the firework had never exploded at all. How wild is that?
Section 3. The physics of collisions. So, what actually happens when our carefully tracked systems smash into each other?
When you look at high-speed footage of a baseball bat violently compressing a ball, it completely reframes what a collision is. In physics, a collision isn't just an accident. It is a very specific event where a massive, incredibly brief external force suddenly alters our target's momentum. During this tiny fraction of a second, the impact forces are so extreme that we can usually just ignore everything else in the environment, even gravity. To mathematically measure that crash, we pull out the impulse linear momentum theorem. It tells us that the change in an object's momentum, that's delta p, is exactly equal to j, the impulse. An impulse is just the integral of force over time. Translating that back to our mental HUD, the size of the momentum spike directly equals the amount of force multiplied by the duration of the crash. So a huge force applied over a single millisecond, or a slightly smaller force applied over a longer time, can actually produce the exact same change in that glowing momentum vector.
Section 4. Conservation of linear momentum. Okay, it's time to dive into
arguably the most powerful rule in our entire diagnostic toolkit.
To unlock this next physics cheat code, we have to run through a quick three-step protocol to draw a bounding box around our colliding objects. First, define the system. Second, ensure it's closed, meaning no mass escapes. And third, this is the most crucial one, ensure it is isolated from any net external forces. If you follow those protocols perfectly, a literal mathematical magic trick happens.
P initial equals P final. For a closed, isolated system, the total linear momentum cannot change. This is the law of conservation of linear momentum. What this actually means is that no matter how chaotic a crash is, inside our bounding box, no matter how many individual pieces are smashing, bending, or shattering, the total combined momentum of every single piece before the crash is exactly equal to the total combined momentum after, period.
Section 5. Analyzing types of collisions. Now let's classify these impacts by checking their kinetic energy stats.
So in an isolated system, momentum is always conserved, no matter how bad the collision is. But whether kinetic energy survives the crash tells us exactly what kind of collision we just witnessed. In an elastic collision, think billiard balls clacking together, kinetic energy is perfectly conserved. In an inelastic collision, energy gets lost to things like sound, structural deformation, or heat. And if the bodies smash into each other and just stick together entirely, that's a completely inelastic collision, where the bodies literally share the exact same final velocity.
And that brings us to this really beautiful realization. If momentum is conserved and momentum dictates the center of mass, well then the velocity of the center of mass remains completely unaffected by a collision in a closed, isolated system. Think about that. While individual pieces of debris are smashing and bouncing in completely different directions, if you track the ghostly center of mass of the whole system, it just keeps floating along in a perfectly straight line as if absolutely nothing happened.
Section 6. Rocket Science and Varying Mass. Let's take these tools up to space and examine the ultimate complex system. Up until right now, all our systems had constant mass. But rockets have varying mass because they are continuously blasting massive amounts of exhaust out the back. To analyze this without breaking our rules, we just redefine our system to include both the rocket and the ejected exhaust. This brilliantly illustrates how rockets use the conservation of momentum to their advantage. By violently shooting mass backward, the system's total momentum has to remain balanced, which literally forces the rocket's remaining mass forward. Following that logic leads physicists right to the second rocket equation. It shows that the final speed of a rocket increases based on the natural logarithm of the ratio of its initial mass to its final mass. Simply put, because the rocket is getting lighter and lighter as it furiously burns off fuel, its acceleration continuously increases, in this beautiful, extremely powerful feedback loop that drives it all the way into orbit.
From the parabolic arc of a wildly flipping bat, to the chaotic crumpling of a one-dimensional collision, and all the way up to a rocket breaking the atmosphere, it really all comes down to finding the center of mass and following the unbreakable rules of momentum. So I want to leave you with this thought today. Look around your world and try to spot those invisible momentum vectors balancing out in real time. If the conservation of momentum is an unbreakable rule, how is it secretly dictating every single physical interaction you see? Thanks for booting up this explainer with me today, and keep looking for the hidden forces just beneath the surface.